Hey physics friends, and I wanted to take a chance to go through the projectile concept check for understanding that you guys had. It's like 30 questions, but they go pretty quick once you kind of have the idea. And the idea is this, that projectiles move forward at a constant speed, regardless of where you're launching it, how you're launching it, whatever. When you ignore air resistance, they go forward at a constant speed. They go up and down, accelerating at 9.8 towards the Earth. So they're not going at a constant speed down, but they are going at a constant speed forward. So they're accelerating down, they're not accelerating forward. And that we're going to just beat that to death here as we go through these. So here we go. Which one hits the ground first? The one that you launch downward. Like if you throw something down, it's going to reach the ground much faster than the next one. A bullet shot from a very high velocity rifle may travel 100 feet or more without dropping? Not at all. The moment a projectile leaves anything, there's no more support on that bullet from the barrel, it starts dropping. Nope, it does not. They don't go straight, they drop immediately. A marathon runner wishes to throw his cup away. He should release it before. If you release it afterwards, it's going to fall. If you release it right here, it's going to fall there. If you release it after you've passed it, it's going to fall there. If you release it before, it's going to fall in the box. So the correct answer for this one is letter A, before. A hunter spies a deer. This is tricky. I read this in Field and Stream magazine when I was in high school, and I didn't believe it, and I thought it was very interesting. Bow and arrows, like a bow, when you shoot an arrow, it drops. If you shoot an arrow straight up in the air, it doesn't drop. It actually goes very flat. So when you aim up in the air, or if you aim down towards the ground, your arrow doesn't drop as much. You could think of a long fishing pole. If a really long fishing pole, if you hold it straight out, it drops a lot. And if you hold it straight up or straight down, it's very straight. And that's the trajectory that your arrow is going to take. It's going to be much flatter. So if you're shooting an arrow that doesn't drop as much, you want to aim below. Believe it or not. It's very counterintuitive. You want to aim a little bit low. This was, in my opinion, this is the hardest question, and I don't know. I didn't expect everyone to get that one, but it's very interesting that you aim a little low. What's the horizontal component? Here we get into the anatomy of trajectory. So when you launch something at 60 degrees, what you're really doing is you're launching it up at 87, and you're launching it forward at 50. That's going to be really important. So the horizontal component at launch is 50. Right there, 50. We're going to use these numbers quite a bit. What's the vertical component at launch? 87. That's the vertical component over here, 87. Oh wait, what's the vertical component at the star? So I take that back. At the star, there is no vertical. It's stopping up and down. So its vertical component is 0 right there. It's not going up, it's not going down, it's stopping vertically. It's still moving forward though, but vertically it's 0. What's the horizontal component at the star? It's 50. Projectiles move forward at a constant speed. So everywhere along this trajectory, the velocity is 50 horizontally. What's the vertical component of the acceleration? It's accelerating down at 9.8. So negative 9.8. The acceleration everywhere, it's always accelerating down at 9.8 meters per second squared. So negative 9.8. What's the horizontal component at the blue circle? That's 50 again, because you move forward at a constant speed, 50. What's the vertical component of the velocity at the circle? It's negative 87. It's kind of a mirror image of the beginning. So when this thing hits the ground, it's moving forward at 50, but now it's moving down at 87. So at the end, it's moving down at 80. So the vertical component is 87. What's the speed? The speed of the projectile at the very end. It's going forward at 50 and down at 87. It hits the ground going 100 meters per second. It's the exact same speed that it was launched at. So the speed is 100. There's no positives or negatives in that one. Would you expect a projectile to go higher or not as high if there's air resistance? If there's air resistance, it's totally not going to go as high up in the air. The air resistance is going to impede it from going so high. It's not going to go as high and it's not going to go as far. Projectiles are really crazy. In reality, it probably goes this far. With no air resistance, they go an insane amount. But when there is air resistance to consider, actual projectiles go much less further than in theory. Is it going to go as far? No, it's not going to go as far. Letter B, not as far. Now we're launching something off a cliff. What's the horizontal component of the velocity? It's 50. The idea is projectiles always move forward with a constant speed. No matter where you're at, they're always moving 50 meters per second forward. So the correct answer for this one, 50. Next question, what's the horizontal component at the start? It's also 50. At the end, we talked about that before, that it's moving forward at a constant speed, 50. What's the vertical component at the start? Oh boy, this is tricky. It's other. We don't know. You'd have to go through some little bit of math to figure this out. Right here at this spot, it's going to be at 87. But now, since you're dropping a little further, it's going to be going faster than 87. So this hits the ground going faster than 87. So vertically, at the top, the velocity is 0. Vertically, at the same height as which it was launched, it's going to be negative 87. And then since it falls a little further, maybe that's negative 150 or something. Again, you'd have to go through a little bit of math to figure out exactly what that one's going to be. So the answer to this one is other. Don't know. What's the vertical component at, 87, negative 87, because it's going to be moving forward at 50. We talked about it having a constant positive forward velocity in the horizontal, but then it's going to be moving down its mirror image of what it was launched at, 87. So this one's going to be negative 87. What's the vertical component of the projectile's acceleration? The acceleration is always vertically, it's going to be negative 9.8 everywhere. So that's going to be negative 9.8. What's the vertical component of the projectile's acceleration? Vertical is always negative 9.8. It's vertically always negative 9.8. And you see how these questions, there's 30 of them, they go really quick because they're hammering the idea that projectiles move forward at a constant speed and they accelerate at 9.8 meters per second vertically. Number one, what's the vertical component of the projectile's velocity at launch? So here we are launching something at a downward angle. So you're going to be launching it forward again at 50, and you're going to be launching it down at 87. So the vertical component at launch in this case is negative 87. So the correct answer for this one is negative 87. What's the horizontal component at launch? 50. You're launching it forward still at 50. What's the horizontal at the star? The horizontal at the star is still 50. Things move at no matter what the projectile is, it's moving forward at 50. What's the vertical component at the star? I don't know. It's more than 87 because it's going to accelerate. So here's going to be one of those examples of other. Something more than 87. It's going to increase its speed vertically. What's the vertical component of the projectile's acceleration? Acceleration is always negative 9.8. So, negative 9.8. Now we go into displacement. So we're going to be doing, what's the vertical displacement from launch until the end? It's 0. If you start right here and then you end right here, vertically, that displacement equals 0. So your vertical displacement, in that case, is 0. What's the vertical displacement from launch until the star? Vertical displacement is 390 because it's going 390 meters in the air, and so that displacement is 390. What's the horizontal displacement from launch until the star? It's half of 890, so 445. So horizontally, it goes this distance right here, which is 445. What's the horizontal displacement from launch until the star? I think it's still 445. I think that's the exact same question as the last one. 445. I'll have to look at that. What's the horizontal displacement from launch until the star? Oh, I wonder if that last question, yeah, it was a cliff, and I just didn't know it. So here, let me go back to number 28. No, it wasn't a cliff. It's the same question. Horizontal displacement, 445, yeah. Must have put that in there twice. What's the horizontal displacement from launch until here? Okay, this horizontal displacement is 940 because you start right here and then you end right there. That horizontal displacement is 940. And then the last question. What's the vertical displacement from launch until the star? Again, the displacement only means what is the difference from where you started to where you ended. And that displacement is negative 100. So you're starting here and you're ending below. So that displacement is negative 100. I hope you started to see some of the patterns, the ideas, main ideas. Projectiles always move forward at a constant speed, and vertically they're accelerating down at 9.8 meters per second, regardless of firing at from level ground, from an elevated position, like positive angle of launch, negative angle of launch. Both of those things are still true.